Okay, so we want to go through one more example. I want us to approximate the error bound in doing the cosine of 0.3 equals that thing. I don't need to say it out loud. Using the Lagrange form of the error. And I just mentioned in class that you would never use Lagrange form of the error for this because it's alternating. We would totally use the alternating series form. But I wanted to give you one other example. Sometimes sine and cosine do not alternate. Like if things are plugged in a certain way, sometimes you will have to use the Lagrange form of the error. So please don't feel like this will never happen. Why is he doing this to us? So first, I sort of want us to remember the formula. What is the error equal to? And I hope that this isn't hard to memorize because it's so closely related to what you guys did in the previous night's homework. Every term of our Taylor series is a derivative over a factorial times x minus c to the same power. Right? So it's going to be the n plus 1th derivative evaluated at z over n plus 1 factorial times x sub 0 minus c all to the n plus 1 power. Next up, we want to make a list of what our variables are, right? So we need to know what n is, we need to know what c is, we need to know what x sub 0 is, and z we should at least make some comment about it. I didn't say it in the setup of the problem because I'm a little bit rushed, but this is a Maclaurin series, so if you're watching at home, keep that in mind. Okay, so hopefully you noticed that n in this problem is 4, because looking at this approximation up here, this is clearly a 4th degree approximation. It's got a 4th power on it. This is a 4th degree approximation. Because it's a Maclaurin polynomial, we know that c is 0, and x0 is the value that's being plugged in. And in this case, that's 0.3. Occasionally, that value will be different than the thing that's up here. Certainly, when it's not centered at 0, there's an example like that in the homework tonight. So you'll see it when you get there. What do we know about z? Z has to be between 0 and 0.3. So now that I have all of that information figured out, I basically start plugging stuff into this. Right? My error is going to be equal to, so my error is equal to the 5th derivative of the function at z over 5 factorial times 0.3 minus 0 to the 5th power. So next up, what is the 5th derivative of this function? So my original function was cosine. If you do 4 derivatives, you get back to cosine again. So the 5th derivative is simply the derivative of cosine, which is negative sine. That means my error is negative sine of z over 5 factorial times 0.3 to the 5th. And remember, my z value is supposed to be somewhere between 0.3 and 0. And so here's the point right here. And I know you guys asked, like, oh, how do I find out what z is? In some sense, you don't even care. Sometimes you just look at this function and say, you know, if I plugged in everything between 0 and 0.3, how bad could this possibly be?
Not bad.
Well, I need a number. The sign of anything is never more than 1. Which means I know that my error certainly has to be less than or equal to 1 over 5 factorial times 0.3 to the 5th. By the way, I got rid of this negative here because, to be honest, all along this was supposed to be absolute valued. Then the key thing is, do you guys understand where I got 1 from? My job is simply to make this approximation as bad as possible. If I wanted to, I could have put in 0.3 there. But the reality is I don't know what the sign of 0.3 is, so it's kind of cheating anyway. Now, you could go with something like saying, well, based on my knowledge of sine, I bet that's not bigger than a half. You could put a half up here. If you can come up with a way to make your worst-case scenario less bad, great. But at the moment, for sure, I can say that my error has to be less than 1. If I throw all of that at the calculator, it'll give me my error bound.